Okay, let me get started with a reminder. Indeed, this afternoon, so there's was the nice initiative that there's going to be a traditional gong show. This is actually a tradition more in the Cargès school, but it's a nice way of just briefly telling your fellow students who you are, what you're interested in, and what you plan to do in terms of your research. If you have something interesting to say about a research topic or a result that you have obtained, you can do that within essentially just 2 or 3 minutes. Probably the first half minute would be introducing, and then you write down the idea, and then that's the end of it. I think it's all done on Blackboard. At least you just chalk, that's the way to do it, over here in Bloomberg Hall at 2 p.m. And there will be a little bell that will tell you when your 3 minutes are up. And again, it's a very nice way of getting to know, because initially, obviously, I assume not everyone knew everyone else, but in the future, one of the very useful things of a school like this is actually to get to know your fellow students, and those are people that will continue to be interested in the same things that you're interested in, and making those connections is for sure one of the benefits of coming to a school like this. And this is a good way of optimizing that opportunity. Okay, so I'm going to continue a little bit on some themes that I started in my first lecture, and preparing some of the things, introducing some more of the ingredients that will continue also into next week. F-theory has been mentioned a few times. Again, next week we'll explain really in more detail what the main ingredients are, and Edward Witten will indeed explain how one can make grand unified theories out of it. But there are a bunch of ingredients there that we sort of want to sort of step by step introduce. Other things that indeed already came to the fore this morning, which definitely is a very important component of whatever you do with string theory and phenomenology, and actually almost whatever you do with beyond the standard model of phenomenology, and that's supersymmetry breaking. And Hans-Peter Niels will be discussing, covering that next week. And Shamit Kashu will also talk about similar issues, symmetry breaking, and also connected to moduli stabilization and cosmology, inflation. Those kind of connections have been developed over the last several years, partly because indeed the added insight of how to think about the landscape of string compactifications in ways where we can start doing a bit more dynamics and ask a few more questions of which things are generic and which things can we control, etc. Anyway, let me get started. This will allow me also to correct a very small mistake that I made earlier. So in order to explain what F-theory is, M-theory is actually a good starting point, and indeed there's an interesting connection between F-theory and M-theory. F-theory is nothing else than a particular perspective on 2B string theory. And when it got started, people kind of associated it even with a 12-dimensional perspective on string theory. So for a while, people were thinking, well, was 11 not enough? Well, let's go to 12. But it's just a clever way of parametrizing still a 10-dimensional theory. But it will become clear in a second why it seemed to be 12-dimensional. And the basic idea, at least if you want to understand the geometric perspective of F-theory, it's one useful starting point is precisely this connection that John actually discovered and also explained in his lectures. If you compactify M-theory on T2, that gives a very useful way of thinking about the symmetries and the ingredients of type 2B string theory on S1, indeed by the idea that the membrane wrapping on one of the circles of the 2 torus would be the string of the type 2B, where the shape of the torus is connected to the strength of the string interactions. E to the minus phi is 1 over GS, but it also has this axion field in it in terms of the angle here That's the axion field. And in 11-dimensional supergravity, this thing has an action which indeed is this very unique 11-dimensional Einstein action plus the supersymmetrization. But in terms of the bosonic field content, there was this 3-form field which actually has some kind of 11-dimensional Chern-Simons type coupling, where this dc3 can be called a field strength of that particular 3-form field. And of course, there's a kinetic term for these guys, but I want to at least emphasize this particular term. Now the fact that there's this 3-form field in the M theory then translates via the dictionary with the 2B theory. Again, you sort of have to dimensionally reduce this 4-form, and you can do it in 2 ways, either along the horizontal direction, which we call the A cycle of the torus, or the vertical direction, which is the B cycle of the torus. And if you do it in those 2 ways, you get 2 components. One is the NS form, 3-form, and the other one is the Ramon-Moore 3-form, which was also mentioned again in the previous lecture. And you can combine them nicely in this particular combination, which transforms nicely under this natural SL2Z symmetry transformations that act on this torus. So you can decompose this G4 like this. And now one important comment, which I think was made, but let me again emphasize it, is that the size of the 2 torus in this particular correspondence, on the one hand, indeed has something to do with the string coupling, at least the relative size between the vertical and the horizontal component, but the overall size of the T2 scales inversely with the size of the circle of the 2B string theory. So that's a very funny geometric correspondence, because it actually means that I can decompactify the 2B string theory, so get rid of that circle by shrinking this 2 torus. So shrinking something on this end, which is sort of like compactifying, corresponds to decompactifying on this end. So in the end, we'll keep this torus, but only the shape of it, not the size, because we've shrunk it to 0 size. But we've gained an extra dimension. So rather than 2B on S1, you really get the 10-dimensional 2B string theory in complete generality. And the miracle that does this is that the 2 brain wrapped on this T on this 2 torus, if the 2 torus shrinks to 0 size, wrapping a brain on something of 0 size costs 0 energy. So actually that M2 brain becomes a very light object, and it simply becomes the momentum, and it was already the momentum along the S1, but if the momentum along the S1, if the S1 becomes very long, then the KK momentum along that S1 becomes very long wavelength and therefore very light, and that's the dictionary. If the M2 brain is perpendicular to the T2, it turns out that the extra dimension that you gain by doing this funny decompactification, or at least taking this particular limit, makes the dictionary such that it corresponds to a D3 brain. And you can kind of see that by going through how all the various forms, how all the things connect to each other. So a particular equation that that I wrote down, which told you about how many D3 brains there are, etc. Let me briefly mention how that can best be understood, also from this particular perspective. And this goes back to earlier studies. There's a very nice paper by the other 2 authors of the book with John, Catherine, and Melanie Becker, who looked at M theory on a Calabi-Yau 4-fold. So if you compactify M theory on a Calabi-Yau 4-fold, 4 means 4 complex dimensions. So this is an 8-dimensional manifold. And therefore, you go down to 2 + 1 dimensions. And if you look then at the M2 brain conservation then it turns out that obviously this C3 field will play an important role then, because the M2 brane, if there would be a bunch of M2 branes, then if I would integrate over the world volume of those M2 branes the C3, that's the way in which an M2 brane couples to this C3 form field. So this is a sum over the M2s. So here I'm not just considering the 11-dimensional supergravity, but with some membranes in it. And it turns out that there's one other term here in some kind of loop-corrected or some higher-order corrected term, and I'm not going to be too specific about it. It's an 8th form that's made out of the curvatures, so it's an r to the 4th term in terms of the 11-dimensional curvature that also couples to that particular antisymmetric 3-form field. And if you take that whole action into account, you get the M2 brane conservation or C3 flux conservation condition, that the total number of M2s plus the integral over this Calabi-Yau fourfold in this case, if you do it in the, of this G4 wedge G4, is equal to the integral over that I8, over this r to the 4th term over that Calabi-Yau, and that turns out to be the Euler number of that Calabi-Yau divided by 24. So this thing here is the integral of this I8 thing over your Calabi-Yau. So this is something that one can understand from the point of view of the M-theory perspective. But now what you can do is you can take a Calabi-Yau, a fourfold, which becomes what we say elliptically fibered. So it locally, it looks like some 6-dimensional manifold times some T2, but only locally. The T2 can vary in shape as you move along the 6 manifold. Maybe this is appropriate notation that you put some semi-direct thing here, but let me not do that. But the point is that if you want to go now to F theory, then you can actually use this same kind of setup, but then indeed you have to keep in mind that you want to decompactify the 2B perspective by taking the limit where this particular T2 shrinks. So if we shrink that thing, the T2, then we obtain a decompactified 11-dimensional theory, 10-dimensional theory, and that 10-dimensional theory will live on that 6-manifold times 3 plus 1 dimensions. So whereas the original theory had only 2 plus 1, M theory had only 2 plus 1 decompactified dimensions, by this step of shrinking the 2 torus, I'm turning that 2 plus 1 decompactified dimensions into 3 plus 1 decompactified dimensions. So that's the M theory, F theory connection, at least in a nutshell. But in the end, even independent of this M theory perspective, it kind of indicates that what F theory is, it's a clever geometric way of combining part of this compactification space, which is this B6, and the geometry of that T2 in a way that makes one geometric, coherent picture. Are there questions about this? Yes? I'm sorry, if this is... F theory, I would say it's just an encoding of the strongly coupled 2B. And let me continue on about saying things about that, because eventually, indeed, what F theory does, it allows you to the 7 branes plus its generalizations in a natural way, in a geometrical way. And let me try to make that particular point clear. First, let me talk about the D7 brane itself. So again, in 2B string theory, just to remind you, there are all kinds of branes, D1 branes, D3 branes, etc. The D1 branes, let me briefly just mention their role. The D1 brane is the strongly coupled dual, the S dual, the G to 1 over G dual of the fundamental string. So these two things form together a S of 2Z multiplet under the S duality, as John explained. Again, these correspond to the M brane wrapped around these two cycles. The D3 branes are self-dual. D5 branes, again, they come in types. We call them PQ5 branes. Meaning, what I'm now talking about is the fact that in 2B string theory, because of this tau parameter, you can actually realize that the whole thing should come into representations of the modular group of that torus. So there are different types of branes. But let me not continue too much about these. These 7 branes also have more general cousins. But the basic branes, indeed, are the D branes, and they are described in the way that John explained in the very first lecture. So let me talk about the D7 brane. And one way of immediately seeing what kind of effect that thing has is, again, looking at its coupling. And one of its couplings, the most characteristic coupling, is the coupling to the Riemann-Moore 8-form field. Now, what's the Riemann-Moore 8-form field? If I take the 9-form field, which is the D of C8, it's the 10-dimensional Hodge dual of the D of this is C0. Because this is a 9-form field, the 10-dimensional Hodge dual will give me a 1-form field. And therefore, that C0 over there, the real part of tau, the D7 brane is magnetically charged under that C0 field. And what that means is that if I have some D7 brane here, then now let's briefly think about dimensions. A 7 brane is 7 plus 1 dimensional, which is 8 dimensional. And it's in a 10-dimensional space, which means there are 2 transverse dimensions. So this blackboard is the 10-dimensional space. That's your D7 brane. And therefore, indeed, if I'm a particle, I can actually move around that D7 brane and have a non-trivial loop. So a D7 brane is like actually, in our dimensions, it would be like a string. And one of the things that it actually does, it has a gravitational field that will create a conical deficit, which I will not say too much about, but it has gravity, and it will create a conical deficit. So although in some cases one can maybe take limits where you can ignore the back reaction of these 7 branes, but generally these 7 branes are pretty heavy objects. And at some level, if you put in flat space, it turns out that you cannot put more than 6, is it 16 or 32? I forgot. 16. I think you cannot put more than 16. It depends on whether you indeed compactify infinity or whether you want to compactify all of space into something finite. But basically, because of the deficit angle, you fold up space at infinity. So you can only put a finite number of these 7 branes in your geometry. But another thing that happens indeed is if I take the value of C0 over here and I would follow it around that loop, it actually doesn't come back to itself. Or more generally, if I take tau and I follow around that loop, it actually comes back to tau plus 1. So there's a branch cut for the value of tau. This is a source term for the value of tau. And tau is multivalued if you go around the D7 brane. Yeah, you get some SL2Z monodromy. Now, tau to tau plus 1 is not too bad. It's just an action on the real component of tau, and therefore the dilaton can just stay constant at that point. But there are more general D7 branes, which we'll talk about more generally, some Q7 branes, where in general, if you start with tau here, that the tau that you end up with is some A tau plus B divided by C tau plus D, where A, B, C, D are integers that in some way are related to that Q D7 brane. So you have some pretty funny objects, and these are definitely strongly coupled objects in the theory, because now tau actually will have to have a singularity at that particular point, where also the imaginary part of tau will have to become big. And if the imaginary part, I'm sorry, even small, or maybe, anyway, it does something funny over there. We can talk about it later. And these things are more complicated. But it turns out actually that if you want to make grand unified models with the content of grand unified theories, you will have to consider these more general kind of branes. But for today, I'll only discuss these, or at least.
Just curious, can you see these monodromies from the supergravity solution?
Yes, there is a supergravity solution that one can try to construct. And in this particular case, the supergravity solution is actually quite beautiful. There's a paper by Vava, Shapir, and Yao that describe the supergravity solution of that D7 brane. Are there other questions? So if I dimensionally reduce, by the way, this formula, or actually go to the F-theory version of that formula, last time I was a bit too quick in writing it down. So I kind of can write it still down like this in F-theory, that now the D3 brane charge of F-theory on that manifold, where I've taken the zero size limit of this D2, there's again this equation. Last time I was a little bit sloppy in writing this as integral of G3 wedge G3, which John correctly pointed out is 0 if I wedge a product thing with itself, because in 3 odd dimensions that happens. I forgot to write down a bar, and then this formula is correct. Or another way of writing the same expression is that this thing is the integral of F3. So this is over the Calabi-Yau 4. This is over the Calabi-Yau 3. Calabi-Yau 3. Sorry, it's not Calabi-Yau 3. It's the B6. It's the base in general. F3 times H3. Now, I should say, though, that in a lot of practical studies of F-theory, in some cases the F-theory-ness of F-theory is important. In other cases, there are particular limits of F-theory where indeed you get these orientifold versions of 2B string theory. So all the F-theory-ness in some level is then being put in certain orientifold planes. Or another way of saying it is that as was also emphasized earlier, for a long time it was thought that these were the only contributions to these kind of charges, and the fact that there's this thing on the other side of the equation was something that was only later perhaps appreciated. But this contribution from the Euler number coming from that form in the limit of orientifold compactifications localizes at the point of the orientifold planes. So the orientifold planes are the only thing that carry the opposite charge relative to the D3 brane charge. Yeah, so maybe I'll give you a reference of that. There's, again, a beautiful paper by Ashok Sen, who explains that there's a very nice limit of that the orientifold planes can be understood as a very nicely as a limit of F-theory. The only thing, again, I can say at this point, and I don't even have deeper understanding of it than that, is that the one can verify indeed that the unitified planes have the opposite charge and as the D3 branes, and therefore locally, if I would have to do the integral over that particular geometric quantity, this I8 quantity over that region, it has to give me that number. And there's no very, I don't have a very better intuitive way of saying it than that. Now, as was mentioned a bunch of times, if I have a Calabi-Yau manifold, or this 6-dimensional manifold over which I do the 2B compactification, then there are all kinds of cycles, 3 cycles. Earlier I was doing an integral over a 1 cycle of this 2 torus. Now I'm doing an integral over a 3 cycle inside of a Calabi-Yau that can give me numbers. Say, for example, there could be some 3 cycle in my Calabi-Yau manifold that gives me a number m for this quantity, and another cycle, which I call a B cycle, which gives me, say, a number k. And then this equation, for example, would look like q d3 plus k times m. And maybe there are other cycles as well, so there could be other contributions from here, but at least one of the contributions of the flux, these 2 fluxes would give me something like that, is equal to that Euler number. And again, one starts talking about the landscape of compactifications by making all kinds of different choices for these m's and k's. And if you have many cycles, there are many ways of doing that.
Is B6 a Calabi-Yau threefold?
No, it's not. It's not Calabi-Yau. There's another condition that it has to satisfy, but the condition actually is that if I would have a particular elliptic, that this whole space as a whole is Calabi-Yau fourfold. In the case where there's an orientifold limit, so that, by the way, in the orientifold limit, these kind of spaces do not have orientifold limits. So if I have an orientifold limit, I only have these kind of guys, these 7s, and I have orientifolds. And in the orientifold, in the cases where there is an orientifold limit, then tau is, at least the dilaton is constant throughout, and it's a solution with constant dilaton. And then, indeed, in that case, the base has to be an orientifold of a Calabi-Yau. So, but more generally, it doesn't need to be. Now, again, we briefly talked, it has been mentioned several times also, about whether or not, when you have these kind of solutions, whether it gives rise to warping or not, or what kind of generic geometries one gets. So if I have my base, again, let me for now go back to this orientifold limit. Let me skip the F-theoriness for a moment. I'll return to that next week. Now, so this is my Calabi-Yau. Let me draw something rather simple. The topology doesn't quite seem to make sense, but this is roughly how it fits in my picture, my mental picture of this. So the A cycle is some cycle that looks like that. And I'll explain later why this thing cannot actually be pulled off here. So it's a non-trivial cycle in my Calabi-Yau. And there's some other cycle, which I'll call the B cycle, that goes like that. And the 2 cycles intersect at one point. I'll have these 2 conditions, that one of them will have flux for F3, and the other one will have flux for the K3, sorry, flux K for the H3. And then if you go through the exercise that I actually did in my previous lecture of writing down what the kinetic energy of the H3 and the F3 flux is, and you minimize that energy, and you can do that with this Gukov-Pfeiffer-Witten potential, or you can just do it by brute force, by writing down those 2 energies and just minimizing it. You'll actually find that because the energy of the 3-form flux comes with this 1 over gs squared in front of it in general, and the energy of this F3 flux does not have the gs, you actually find in general that this B cycle is going to be much longer than the A cycle. And another thing that will take place is indeed that you can just look at the equations for the warp factor, that indeed the metric that you'll find, the 10D metric, will have this shape that there's some radial direction, which is going to be that radial direction, where it will roughly look like some ADS-like space, this region, times some 5-dimensional transverse slice over here. And what you'll find is that the amount of warping between this and that point and say this point over here, roughly what I mean by the amount of warping is how small is this number, e to the minus alpha r, how much redshifted am I when I'm down here compared to when I'm down there. So how much scale is involved in this whole thing? And the number, I think, is something like 2 pi k over GSM.
So here the warping is due to the flux?
It's due to the flux only. There's no brain in this context. So here you can see roughly what you would need to do in order to get either big or small warping. Actually, you don't need to do much to get big warping, assuming that indeed in these models it is possible to stabilize the dilaton. But assuming you do that at a small value, like a tenth, then I already have a pretty big number here, like 20. So if k and m are of comparable order of magnitude, then you have large warping. So it's rather generic that you would get it. I will not say too much about the actual interpretation of what's going on here. It means actually that you're close to something that's called a conifold singularity. And it even has, indeed, a very specific gauge theory interpretation. Again, we haven't been saying too much about ADS-CFT. Probably next week, Shamus Kashru will say a few more words about ADS-CFT. But it turns out that that conifold singularity can be thought of as something that's a particular gauge theory. And Klebanov and Strassler, they studied that singularity and the dual gauge theory. Maybe I'll just mention their paper as a reference. Let me just make one particular comment about this, is that if I would say, if I cut open this Calabi-Yau space, and let me assume that all the orientifold, all this negative charge, so here are the O planes that carry negative D3 charge, and let me assume that there's no orientifold stuff happening down here. Which means that if I look at this particular integral, indeed, at the moment, I'm not considering any D3s, so let me have only flux. But then, effectively, that flux, this particular flux, this particular contribution to the flux, will still have a non-zero integral over this region. And what that means is if I take this particular slice, that I can integrate F5, the 5-form flux, which normally would tell me what the effective D3 charge is. If I integrate that over this 5-dimensional manifold with some 5-dimensional metric, I'll get a number which is some k of r times m, where that k of r starts with 0 down here, but it becomes k once I get down here.
So normally you need some symmetry for your open, so you need some tattoo reflection or some point reflection in the convex space. So how can you move them to the outside?
I'm sorry, what are you worried about?
Usually you need some symmetry of your background or not. If you have oriented projection.
If I want to have these O planes? Yes, there's a symmetry.
But now you're assuming that it's somewhere sitting.
It's not that hard to draw that. I can draw something that, okay, it's actually very hard to draw it, but imagine that this is exactly equal to that.
So you have another side.
I have some other side, and then I divide it out, and I'm not drawing the other side. So I'm just folding this thing up. I'm just folding it up. And that, so you have to start indeed with a Calabi-Yau with a Z2 involution. So it's no, right. So at least whenever you have an orient default space, you have a covering space, and you have the base or whatever. After dividing out the Z2 transformation, you have the base. Here I'm only drawing the base. So, but indeed, if you have an orient default plane, orient default construction, you need this other thing over there. And generally, it's actually sufficient to have only one Z2, although in some cases Z2 times Z2 can be useful. But having one Z2 projection is often enough. So you need one Z2. But OK, so what I'm saying here is that the flux itself effectively builds up this D3 brane charge. And there's even a very direct interpretation of this via ADS-CFT, that the region, the large warp region down here with large warp factor, really represents some kind of strongly coupled gauge theory with a rank that's equal to that. This is the rank of that particular gauge group. And that rank of the gauge group, strangely enough, depends on that radius r. Again, this Kelvin and Strassler explained very beautifully why that happens. Because it turns out that that particular gauge theory is what's called a cascading gauge theory, whose effective rank indeed depends on the energy scale that you're looking at. But OK. Probably next week there will be some more discussion of that. OK, why am I mentioning this? So I would say there's one other important motivation for thinking about compactifications in a way when one starts really separating things out as being localized within the extra dimensions. And some of that has to do precisely with the topic that we started talking about also this morning. And part of that motivation also comes from supersymmetry breaking. So there's essentially, both from a practical point of view in string theory and also from a phenomenological point of view of trying to make models that are models of particle physics. So from the bottom-up point of view, there's the following, you can call it a paradigm, where supersymmetry breaking typically divides things up into a visible sector, which would contain the MSSM, could be the MSSM or something bigger. And then there would be some hidden sector where the SUSY breaking takes place. And that SUSY breaking then gets mediated to the visible sector. And that can be done by many ways, either by all kinds of gravity or by anomaly mediation or etc. So we'll be talking, Peter Niels will be talking more about that. But one of the things that it already indicates is that you want to have some kind of rationale for why the SUSY breaking is, in what way is it actually separated from the visible sector? What separates these two things? Now, in the heterotic string in the old days, that separation was very naturally accomplished by the E8 times E8 structure. The fact that the gauge group had the two E8 factors. Later, it was understood that if that heterotic string in the strongly coupled limit becomes M theory with an interval where you have a brane sitting on one end and another brane sitting on the other end of the interval, which this is one E8, that's the other E8, and then indeed that E8 times E8 separation became a geometrical separation where indeed the SUSY breaking would initially take place down here and the visible sector would be down there. So much more generally, once you've reached that stage, and you have the capability of localizing your matter and your dynamics in regions in your actual dimensions, it becomes natural to make that a general kind of idea that the hidden sector might be geometrically separated from the visible sector. And to make this separation in terms of quantum field theory, low energy effective field theory, something that can be understood from a higher dimensional perspective. Now, so SUSY breaking has some effect on phenomenology, obviously, which was discussed also this morning, and that's one of the things we want to compute. Another effect that it has is precisely it has an immediate effect on your story of do you actually have a compactification or not. Because for many years in string theory, we only understood supersymmetric compactifications, and the reason why we only understood supersymmetric compactifications was as soon as we would have some non-supersymmetric dynamics, basically you would either get tachyons or you would get this runaway behavior where basically the compactification would no longer be stable. It would just decompactify and roll back to maybe 11-dimensional supergravity. So there was no controlled way of doing supersymmetry breaking. And the SUSY breaking, at least now, maybe there are various ways of doing it. In the old days, there was the Schwartz sort of boundary condition way of doing it. But again, that thing, I think people, when you analyze it, has these kind of instabilities. But a more controlled way of doing it would actually be to be using something like this. And there's one example, which indeed is now used quite a bit, that I introduced with Pearson and Kashu several years ago. And then the next year with KKLT, they actually embedded that in that particular non-compact setting, where you just put a particular non-supersymmetric object at the tip of this particular geometry. So the idea is to just put an anti-D3 brane down there. Now, why is that good? Because this anti-D3 brane basically will sit on a rather smooth geometry. Let me be a bit more specific about what the geometry here looks like. If I cut this thing open here like that, this 5-dimensional geometry, K5, whatever, if I cut this thing like that, looks like an S3 times an S2, where this S3 remains finite at the tip, and the S2 looks like this. The S2 shrinks to a point at the tip. So this anti-D3, and you can actually look at it dynamically, will indeed be pulled down the tip because of the F5 form flux. Actually, this force of the F5 form flux will pull it down towards the tip, and that's where it sits. It cannot do anything. And you can even understand from this Klebanov-Strassler gauge theory to some extent what kind of gauge theory corresponds to this particular object. And in gauge theory, you're not afraid to break supersymmetry, and therefore this thing is what we call metastable. It's a metastable non-SUSY state.
Which SUSY are we talking about? N equals to what?
Okay, by the time that we've done the Orient default, we're only talking about n equals 1. N equals 1 in 10 dimensions, but I'm sorry, n equals 1 in 4 dimensions also, because you start out with 2B string theory, indeed, in 10 dimensions, which has n equals 2. It's a non-Carl, but then you go to 4 dimensions on a Calabi-Yau, where you remain with n equals 2 in Calabi-Yau. But the fluxes, actually, I should say this, is that the 3-form fluxes and the Orient default, they break it down to n equals 1. So the 3-form fluxes, they either imaginary self-dual or imaginary anti-self-dual, and whichever the two of which you choose there determines which supersymmetry in 4 dimensions is preserved. And my definition of what I call an anti-brane or a brane has to do with that particular notion of self-duality. So this anti-brane would then be incompatible with that notion of duality, self-duality, or if it would be compatible, it would be a D3 brane. Could I write an effective term? Now, if you would use the equations that were on the slides this morning of how fluxes lead to soft terms on world volumes of branes, what I could do is I could actually turn things around. Let me initially turn off the fluxes. Let me take this D3 brane. That D3 brane in itself would not break supersymmetry. That's not right. It's only anti relative to the flux. There's no such thing as an anti-brane relative to the geometry. So for the Calabi-Yau, I could simply take this anti-brane here, and that anti-brane itself still has supersymmetry. That's okay. Locally, obviously, I can study that, and then indeed there could be an incompatibility indeed between those O planes and that thing as well. And again, let me say it as follows: in terms of the so the question that you're asking is the following. Partly is well, is this explicit supersymmetry breaking, or is it dynamical supersymmetry breaking, or is it F-term, or is it D-term supersymmetry breaking? How does one write down the effective field theory? Actually, it turns out to be a relatively subtle problem indeed to write down that particular effective field theory. But that doesn't take away the fact that this is a metastable non-supersymmetric state. I should, yes? No, what it actually means indeed is that, okay, well, this charge becomes -1. So you just make sure that these numbers add up to a way that actually makes sense. Now, for KKLT, the motivation, by the way, of introducing this anti-brane was not only to break supersymmetry, but actually the added benefit of breaking supersymmetry was that their particular model also got a contribution to the cosmological constant that was positive. Because their initial model had negative cosmological constant because it was supersymmetric, and every supersymmetric compactification to 4 dimensions has either 0 or negative cosmological constant. And this is one way of making metastable vacua the zither space vacuum. So KKLT, they had a metastable vacuum, the zither vacuum. There's another question over there.
Why should Susie breaking not be explicit?
Yeah, it's always a question of, in the end it becomes a question of words, whether it's explicit or spontaneous or the reason I can tell you why it's not necessarily explicit is because this theory that one describes down here actually also has a supersymmetric ground state. And this thing can actually decay to a supersymmetric theory where essentially the anti-D3 decays in D3 branes in a funny way that preserves that relation. So you can view it indeed as a state in a supersymmetric, as a non-supersymmetric state in a supersymmetric theory. Yes, in a dynamical way. There's in principle, you can start with a supersymmetric theory, turn on certain VEFs, and then put yourself in this particular point. I can discuss this later, but there's a process that we call brane flux annihilation, where this brane, because effectively, as I've been explaining to you, is that this throat represents the D3 brane charge. So what I'm looking at is a configuration that carries positive D3 brane charge, and I'm adding some negative D3 brane charge in it. And it's actually possible for this object via some tricky process to annihilate against some of this stuff. But that's a metastable process. At least meaning it's a process that needs to take place via tunneling. So there's a potential barrier against doing that, but it can actually do it. And it's not that basically what will happen is that this k will actually go to k minus 1. Which means that I have now m D3 brane charge, and it turns out that that situation with one anti-D3 brane can tunnel to this particular situation, where I have m minus 1 D3 branes.
This D3 brane charge is not due to D3 branes exactly? Or?
It's not due to D3 branes. It's completely encaptured in the presence of flux. But it turns out, so by the way, one way of thinking about it is as follows. So sorry, I was saying, well, actually what you want is a process where k jumps by 1 unit, okay? So how would I make this flux k jump by 1 unit? Okay, I have magnetic flux here. How would I make that magnetic? Suppose it's the quantized magnetic flux, a superconductor with a quantized unit of magnetic flux. How do I make the flux jump? If I would have a monopole, I would take it out of my pocket and I push it through there. So, and in string theory, actually, we do have the monopole that's associated with that particular charge. That monopole, that magnetically charged object, is the NS5 brane.
I'm confused. How do you have a flux without an actual source? So usually you have you integrate the E field over the boundary, you find that there's a charge in there, and here you say there's no charge in there.
No, it's the same thing. If I just take a sphere and imagine that that's your universe, so you're not going to ask what's above me. Okay. You're living on that sphere. Then there can be magnetic flux in that sphere. Of course, you as a wiser three-dimensional person will say, "Hey, there's a monopole inside of it," but you don't see it. Yeah, you can have fluxes, and those are quantized. That's exactly what a superconductor does. You can have quantized fluxes. But in this case, actually, the process that makes this thing decay turns out to be a process where you nucleate a 5 brane, an NS5 brane. The NS5 brane will unwrap itself over this A cycle, and thereby create a jump in the flux in that thing. And when that thing jumps in the process, it also creates these MD3 branes, and then one of them can annihilate with that particular thing. So that's the process. But in the end, the key statement is not so much perhaps how it decays. The key statement is that this thing is metastable. Of course, KQLT led to a lot of discussion because of the combination of two things. One is that there was this metastable way of making de Sitter space. You can stabilize moduli, but you can do it in a gazillion ways. And of course, part of the reason for why that discussion took place was because of a very important experimental fact, namely that we now, at least there's quite a bit of experimental evidence that we live in a de Sitter space, that there is a positive cosmological constant, although that value of that constant is exceedingly small, this anthropic type of arguments, we're saying, well, maybe the fact that we have so gazillions many possibilities, maybe someone just decided that people should be able to live in this universe, and therefore chose the constants in a way that all those things conspire to give a very small cosmological constant. From the point of view of string theory, though, the more practical thing that KQLT were able to do here is to separate scales between the issue of moduli stabilization. So the moduli stabilization took place in terms of potentials whose characteristic scale was the string scale, or the compactification scale, which was of large scale. And of course, it would have been bad if by introducing the anti-brane, they would not have been able to, they would have to go back to this discussion of moduli stabilization and say, well, actually, we don't know if you can actually still keep it stable while having the anti-brane there. But the fact that the amount of energy that's contained in the anti-brane is all localized and also small, that allows you to separate those issues. Again, moduli stabilization and SUSY breaking can again be separated in situations like this, where the scale of SUSY breaking is sufficiently small compared to the scale of moduli stabilization. So that's an important point. Okay, I'm taking a little bit more time than I had intended. I think I can still take 10, 15 minutes, and then we'll have 15 minutes where questions can also be asked for Lewis's lecture. So that's how we're going to close off the morning. I'll say a few words about what we'll get started on next week, unless immediately there are questions on this. Okay. So the conifold is one example of a singularity that let me erase this. Everyone has noticed this 2 p.m. in the Bloomberg room. So more generally, one can consider a local singularity in in a Calabi-Yau manifold. So locally, we're looking at a part of a geometry that looks like a singularity, and what it will look like, it will look like this. There will be a thing that I'll call the base of the singularity, and this space will sort of look like what I'll call a complex cone over a base. So the whole cone I'll call Y, which is a 6-dimensional space or a complex 3-dimensional space, and the base will be 4-dimensional. Okay? So then there will be a radial direction, dr squared, but there will also be an angular direction associated with that particular r. And combined, that r will, with that angle, will be some complex coordinate. I'll tell you what eta is in a second. So again, this is the metric on the base. So it's some 4-dimensional metric. So this looks indeed like a cone in the sense that radial direction times some base. Eta is something like a third d psi. So psi is the angle, some angular coordinate that complexifies that coordinate r. And this is 1/3 plus some omega and, sorry, plus some, what is it? Sigma, so it's some 2 form where the d of sigma is, and I admit that I need to, there's some pre-coefficient which I briefly got confused about, but essentially the d of that sigma is the Riemann 2 form, curvature 2 form on that base. This is some kind of Kähler manifold with RAB is proportional to GAB. So it's some Einstein Kähler manifold, and the sigma, the d of that thing, is that particular 2 form. So this is a 1 form, and you put it in here. And it turns out that if you have that particular metric like that with the appropriate relationship between this object and that manifold, then this is a Calabi-Yau cone. Okay? And so what you can now do is you can play a rather general game where indeed if this base, if this manifold X, it turns out has positive curvature, that's what a cone looks like. It looks like a base which has positive curvature with something that spreads out above it. So for every kind of manifold that you can think of that has this positive curvature, you can write down this particular cone. Now, it turns out that there are actually not that many choices one can make, and there's a general class where X is what's called a Del Pezzo service.
Is this related to the B6, the base that you were talking about before, or is this totally different?
It's a similar kind of story, except this is going from 6 to 8 dimensions, and this T2 is being used to parameterize the dilaton, the axion. But the kind of geometric, let me just say this, that the kind of geometric conditions that you would have to satisfy of how this particular thing has to fiber over that in order to be a Calabi-Yau space, for sure. That's similar to what you have to do here. But here I'm already again down 2 dimensions. I'm forgetting about the dilaton and the axion, they're just constants, and I'm just looking at the 6D geometry. In the case of F-theory, indeed, you may need to, again, combine all those ingredients. And it turns out, so in here, I'm briefly talking about the Calabi-Yau. Next week, yes, then you have to combine both ingredients when F-theory is being discussed. Yes?
Is every local singularity of Calabi-Yau
I wouldn't dare to say that. But it turns out that, let's say it this way, every conical singularity essentially looks like this. Now, then once you have a conical singularity, what it means is that this base really shrinks to a point at the tip. So it really really has a point to it. But in general, you can start resolving or deforming singularities, and you can maybe even put fluxes on it so that this cone-like structure will start to deform slowly, etc. So this is a very idealized class of singularities where everything just looks like a cone. Yes?
So you said that for every four-dimensional manifold, it's a property you can construct such a cone, is that what you said?
No, I said what you need is actually a manifold which is Einstein-Kähler and needs to have positive curvature. Otherwise, you cannot shrink it to a point. So there are already some restrictions on what kind of four-dimensional manifold you can put there. I wouldn't be able to say whether this. I don't think this is the most general class of singularities one can consider, but it's a rather general class. Just like in 2 dimensions, you have many Riemann surfaces. But Riemann surfaces with handles typically have negative curvature. They cannot have positive constant curvature. And the sphere is the only thing that has constant positive curvature. So that's a pretty unique surface. The Del Pezzo surfaces are a little bit like the spheres of 4D manifold. It's the generalization of spheres from complex to 2 complex dimensions. So these are 4-dimensional manifolds. Another nice thing about them is essentially that this number n cannot be arbitrarily big. It can go up to 8. It turns out that if n, in principle, you can define it for n bigger than 8, but then it no longer satisfies the property that it's positively curved. And roughly what you can do is if you start with the biggest one, the so-called Del Pezzo 8 surface, then you can take limits of it, you can shrink certain parts of it, and obtain the lower ones. So in that respect, there's a relatively unique surface which is called the Del Pezzo 8 surface, where this n is equal to 8, where you're at least covering a pretty large class of possible constructions of this type. Now, one of the things that I started doing a few years ago is to simply ask the question, okay, well, if it's true that, so if I would take a brane near one of these singularities, let's just try to map out, initially at least, what kind of field theories one gets by putting a brane on a singularity like this, and does it contain theories that actually look interesting enough to be closely connected to the standard model. I will not explain the whole program, but let me be very quick, make one particular point. This is not something that I can directly explain, but roughly the intuition behind it is as follows. So one class of singularities that you could consider would be an orbifold singularity, where I take an origin in space, and I'm identifying points that are identified with a certain discrete symmetry relative to that fixed point. What that means is if I'm a brane, a D-brane, and I come close to that particular point, I'll see all kinds of image branes next to me. So therefore, the open strings that will live on that brane will not only return to the same brane, but they will also connect to other image branes. So the gauge theory on a brane on a complicated space like this can look rather more complicated than the gauge theory on a brane when it's just at a smooth point in space. Geometrically, the way this is being phrased, and this is done in work by a number of papers by Michael Douglas in the early 2000s, and a bunch of other papers. Mostly, again, Douglas developed a lot of this stuff. So a D-brane at a singularity splits up, and the name that was given to it were fractional brains. And again, my own intuition is that basically those fractional brains are linear combinations of these image brains. Because if you have an identification near the singularity, brains will see images of themselves, so the open strings can do more complicated things. Now, so the fractional brains, what they will come like, so maybe I should give them a name, whatever, curly F, I don't know any other name, Fi, but it turns out that if I have, they come so the base X will have some homology classes, and I will have one fractional brain, at least let's say this way, these things form a basis of the homology classes of X. But which basis they'll form will actually depend on the shape of X, namely which basis is actually stable. And what I mean by the fact that they form a basis is the following sense, is in the following sense. So this Del Pezzo surface has a 4-cycle, which is X itself. Okay? It turns out that there are n plus 1 2-cycles, and next week I'll say more about the geometry of those 2 cycles. So what it means is I have this 4-dimensional surface, and there are certain cycles you can put on this, which are 2 cycles. And just on the Riemann surface, you can have many 1 cycles. You have many 2 cycles on this 4-dimensional surface, and there are n plus 1 of them. And of course, there's just 1 0 cycle, and that 1 0 cycle is just the point on that manifold. And it turns out there are no 1 cycles and 3 cycles. So it's only even cycles that exist on this Del Pezzo surface. Actually, the even cycles are the only ones that are relevant to us. And why is that? The reason is that in 2B string theory, what we're looking at here, I should have mentioned in 2B string theory, that's the relevant point, is that I can have the 7 brains, I can have the 5 brains, and I can have the 3 brains. Again, there's space-time filling, meaning that this thing is 4-dimensional in terms of the internal dimensions. This one is 2-dimensional in terms of the internal dimensions. And this one is 0-dimensional in the internal dimensions. And of course, all these brains can wrap certain cycles. So I can have a D7 brain wrapping this thing once. Or I can have 5 types of D5 brains, or no, sorry, not 5, n plus 1 types of D5 brains, because those D5 brains can wrap any of those cycles. Or I can have 1 type of D3 brain, which is just, I put it at a given point. And one of the important things, at least, that happens on a curved space is that the stable brains, the things that actually will be eventually responsible for the gauge symmetry, the enhanced gauge symmetry, like the UN gauge symmetries of the gauge theory, will not be the individual brains over here, but there will be those particular fractional brains.
So when you say they're fractional brains, you're saying that the Pezzo surface itself is some sort of orbital fixed points or some symmetry?
Yeah, at least that's actually how I sort of stumbled on those manifolds, because there was a paper by Bernstein and collaborators, Jajala and Rob Lee, who a while back had some funny SU3 orbifold that led to a rather interesting standard model-like gauge theory. And then I realized that, okay, well, if you do things just with an orbifold, that's way too special if you want to make a gauge theory just with an orbifold, because an orbifold directly comes with very special relationships between various couplings. And the standard model doesn't have those relationships. So you would immediately have to start deforming the orbifold singularity. So you can have an orbifold singularity, but that orbifold singularity has deformation parameters. And therefore, even if you start with an orbifold, after deforming it, you have to generalize it to a more general metric like that. And it turned out that the singularity that they looked at was actually a Del Pezzo singularity. Now, the reason it was actually the Del Pezzo H singularity. The funny thing is that the way I discovered that was not by looking at the geometry of those deformations, it was actually by looking at the gauge theory that you get from the orbifold and comparing that with the gauge theory that you get from the Del-Penzian surfaces. So often actually the gauge theory that you get by putting a brain on a singularity is often a more useful way of actually understanding the geometry of that singularity than the geometry of the singularity itself. So it's a way of probing the geometry of the singularity. Maybe I'll stop here. In the end, what you get is when you have these kind of brains, these types of ingredients, you get a particular set of rules. Basically, this is going to be a toolbox by which you can start building gauge theories. And maybe let me end with one general comment. This is indeed a technology that was also developed by Moore and Seiberg, at least a terminology that they used in physics, known as Quiver gauge theories, which is the kind of gauge theories that you get indeed if you have orbifolds. And basically, you rather naturally get them from these kind of constructions, so what they are. So the gauge group typically looks like that. Or you could have also SO2Ns. And actually, in principle, you could do more general, but if you look at the Quiver gauge theories that come from gauge theories, you would have SP2Ns or USP2Ns, SO2Ns, like that. But let me focus on those guys, which come from oriented constructions. And then because these brains, so what these NIs are, they will tell you how many of these brains I have. So if I have NI of those brains, I have a UN gauge group. And therefore, I can build a gauge theory of that type. Given how many cycles I can have many gauge group factors. And then the intersection number between brain I and brain J will tell me how many bifundamentals there are. In the NJ bar representation. And that intersection number turns out to be the D7 brain number of brain I times a special D5 brain number of brain J. There's a special cycle that intersects with this manifold minus D7I D5, Ji. So that's how you obtain a particular number. For those who know this kind of stuff, this brain, phi brain, is wrapping the canonical 2-cycle within the base. But with these kind of rules, you can start building gauge theories. And let me just mention the following, is that the standard model again fits those kind of rules. Now, in the case of the standard model, where you only use oriented brain constructions, then you use UNs. But it turns out you can actually write down a very minimal version. And this is where I'll end, which actually has not been constructed yet from brains. But I call it maybe a minimal Quiver representation of the standard model. And it looks like this. Here I'll take U3. Here's SP2. Here it's actually SO2. It turns out to be not U1, but okay, big deal. So here we have the quarks, left-handed quarks, up, down. Maybe I have it reversed, but okay, something like that. So these are the C versions of the other guys. The leptons sit here. The electron fields go like this. So this is the fact that there's an arrow here tells me. So what I'm looking at here. Okay, sorry, I should have explained this obviously. So this quiver is that diagram. And the rule for drawing that diagram is to just say, well, if I have a gauge group factor, I draw a circle and I put a gauge group in it. And if there's a bifundamental that is charged under those gauge groups, meaning it is charged in the fundamental of one and the anti-fundamental of the other, I draw an oriented line, because there's obviously an orientation here. But in the case of orientifolds, it turns out that both orientations need to be included, because the open string can connect both between two branes or between the brain and the on-the-orientifold image of the brain. So there are two types of lines you can draw. And so here, this is a line that doesn't connect with itself, but connects with the orientifold image of the brain. So that's why these arrows sort of do something funny. But there's also another guy that does this, which is the N, the neutrino. One of the right neutrinos. So this is the standard model. I'm sorry? Yes, it doesn't have the Higgs yet. The Higgs turns out to be the only line that's not chiral. So there are two lines, H up and down, if you do it supersymmetrically, that reconnect this with that.
You have an extra U1 here.
Yes. So indeed, the person that's the first thing to note is there's an extra U1. That U1 is massive, and therefore, is anomalous. And if you would make a brain construction that would make the standard model like this, it would immediately just become massive. So if I just make the rule that only non-anomalous U1s would be the ones that really would be gauge symmetries, and the anomalous U1 would be the one that would be a global symmetry, then this is actually the standard model.
Do you have a brain model which realizes this Quiver?
We have a lot of students here who can find it for us. And that's homework. So, by the way, so this may look like, okay, some crazy string theorist writing down a crazy diagram way of thinking about the standard model, but forget about string theory. All right, this is the standard model. I'm just introducing a geometric way of thinking about the standard model. For me, actually, these kind of diagrams sometimes are actually quite useful. This is one way of representing the standard model. You can do it slightly differently. For example, I understand R parity. I understand all kinds of symmetries of the standard model much better if I just draw things in my mind like this. And maybe everyone, even without drawing them in their mind, who's thought about the standard model, organizes the standard model in this particular way, in a sense, because you know that the quarks have those quantum numbers. You know that these things have quantum numbers, and just by drawing them pictorially is a very useful way of doing things. But those pictures actually immediately have a translation in terms of the geometric quantities by saying, well, okay, those are branes, those are open strings that are connecting them. But the fact that I'm using that language, unless I'm actually doing something with it, I could also just say, well, let's just stick to the quantum field theory language. But indeed, if you would be able to make this thing in a very practical way with branes, then at least we can close one chapter in the history of string theory where we say, hey, at least we satisfy what's usually called the correspondence principle. And I should say this is a bit of an important point of this whole bottom-up approach, is because one of the criticisms that string theory has gotten was that it seemed like it was this particular very wild jump. Quantum mechanics was obviously considered in the old days as a very radical theory, but it still satisfied the correspondence principle that there was a limit of quantum mechanics that's classical mechanics. String theory seemed like this. Of course, we knew that a limit of field theory was quantum field theory, but we have not been able to show that the standard model is a limit of string theory. And just being able to show that one can get the standard model as a limit of string theory, at least we can say, well, we're back in where conventional physics takes place. That any time you have a new idea, that at least you have the correspondence with the old theory at hand. So it means that any prediction that the old theory could make at least is reproduced by the new one. Of course, the next level of criticism, or at least that you would have to answer, is can you do anything beyond the quantum field theory approach itself? And anyway, that would then be something you would have to address later on.
So this gives you the gauge structure of the theory. This presumably is the MSSM, right?
This is the MSSM with, indeed, as you said, this additional U1, at least represented in the diagram.
This gives you the gauge structure of the theory, but then where do you see Kalkup or something?
So you Kalkup, oh yeah, I should say this. any oriented triangle that you can find in this Quiver diagram where the arrows, okay, I have to, yeah, in this case, although oriented here is not that obvious because of the orientifold business. But in this in the oriented quivers, basically for every oriented triangle, you would actually have the corresponding Yukawa coupling as a classical component in your field theory, in your string construction.
You don't have a triangle for your electronic Yukawa coupling. Have a lamp. The right-hand electrons come from sort of seven.
Right. Yeah, as I said, this is only one way of drawing the standard model. You can draw it in other ways, where indeed actually every Yukawa coupling in principle would have an oriented triangle, and then you could classically write those things down.
Okay. I don't understand that, because when you could make infinite many couplings, so they can go in infinite times in a group if you want.
Those are non-renormalizable couplings. And those indeed are there in the standard model, but they're very small for very good physical reasons. No, the rule for which. Yeah. So again, I should have said the rules for which things are renormalizable and relevant or irrelevant go through the same way as in other. Yes. Yeah, the two Higgses. So actually, what they are. So what it actually is there's one like this and there's one like that. And the reason why I sort of separate this out is that this guy is actually a little bit special in this case, because all the other lines, they have to stay massless because they cannot develop a mass term. So the mu problem for the standard model in this diagram is actually the fact that if I have a line like that and I have a line like that, then you would have to come up with a symmetry reason for why there wouldn't be a mass term that pairs them up. And why are those things light? And again, here you got here's the graphic representation of the mu problem. These lines, they tend to pair up, and you have to explain why they are light. Yes?
One question is so you have those fighter in the seventh brain. Are they basically run off under the cycle to get the...
Yeah, so the seven brain, so I should mention this. So in the most bottom-up version of doing these D-brain constructions, you would say that these things indeed would all be wrapping this base. So all these brains would just be here, and there would be nothing there.
So it's obvious they all satisfy the symmetric condition.
So one thing that will be obvious is that at least if the brain construction does not lead to an anomalous gauge theory, which the thing will prevent you from doing, then the flux, all the flux escapes and tadpole conditions can be satisfied just by doing whatever you do on the other end of the compactification manifold.
Does your theory predict the exhaustion?
I don't have a theory at this point. I just gave you some general rules. These are your cookbook, or at least what is it? Your ingredients, and then you have your recipe, and then you have your dinner. And then, whether the dinner contains exotics, let me be honest, at least if you do this oriented construction, one immediate inevitable consequence of oriented constructions is, for example, that you have two Higgs doublets per generation, simply because of anomaly cancellation. This was indeed mentioned. If LHC starts to find Higgses for one Higgs for every generation, then for sure I'll be taking a more serious look at those kind of compactifications. But it's not again, it's not an inevitable prediction, but it seems to be a rather natural. By the way, a lot of string constructions do lead to Higgs replication with family replication for Higgses. So that's maybe the most generic exotic. Another exotic thing that typically might happen in these things, which I didn't get to, which I'll explain next week, in connection also with F theory, is that these things often indeed lead to other U1s. And there's a very specific way, which is also explained by Luis Ibanez, how ensure that under certain topological conditions that only hypercharge is the massless U1. But who knows? There might be another U1 that actually is relatively light. And one of our most lucky bets in terms of what LHC might do is that there's actually a Z prime boson being found. And if a Z prime boson is found, and again, I'm also going to look back at some of these constructions because it seems to be a rather generic element of this. Oh, the number of generations. Okay, this is actually an interesting question. There's an early construction also of brains at singularities, a standard model type gauge theories by Lewis and collaborators, which made use of a Z3 orbifold. And these kind of things actually do often lead to models with 3 generations. And in that case, this 3 actually seems to have to do with the fact that there are 3 complex dimensions between 4 and 10. So the 6-dimensional manifold is 3 complex dimensions. On the other hand, if you start really enumerating all the possible things, for example, this paper that I briefly mentioned in the discussion earlier of 1 in a billion, namely that only 1 in a billion brain constructions even looks like the standard model. It turns out that getting the standard model gauge groups happens much more frequently. Getting 3 generations is the thing that cuts it down to 1 in a billion. So sometimes, depending on what kind of ingredients you use, getting 3 generations is a pretty hard thing to do. And in other cases, it's not that hard. But it depends on the construction. Are there more questions also for Lewis? Because we can take 5 more minutes to sort of close off the morning session of this week. And then this afternoon, again, I mentioned there will be the gong show. What the arrows represent, I should have said this, I write it in lines, is that the arrow is a line that starts with the representation where there's not a bar and ends with the gauge group for which it is the anti-fundamental. So when we say bifundamentals, we say it transforms in the fundamental of one of the gauge groups, it transforms in the anti-fundamental of the other gauge group. So whenever there's a line with an arrow here, and maybe I should have switched the lines to get conventions straight, the arrows, but it means that it's in the fundamental of one of them and in the anti-fundamental of the other.
Right, but if you have an abelian group, then you have no compensation.
The abelian group actually does come in these kind of constructions rather naturally with a particular quantization, quantized charge. And also in that case, you can say, well, there's the positive charge and there's the negative charge. And those things either add up or cancel in these lines. For example, this E thing here actually has charge 2 relative to this thing. And this N thing has charge 0 relative to that. Okay. Any more questions? Okay. So there's lunch break, and then in Bloomberg Hall over there.